Welcome back. Now that we've got the first and second law sorted out and we have a clearer picture of those laws, we combine them together to make what are called thermodynamic potential functions. And these are very similar to the idea that we had in Chapter 1 when we saw the potential energy function. From that function, we were able to work out the forces that would act on a particle and push that particle towards points that we would call stable equilibrium points. We had unstable equilibrium points, we had stable equilibrium points. And we saw how from that potential energy surface, we could see which direction the system would go. So it's very similar in that sense that we use the term thermodynamic potential. So given what we know, we have the second law here that the ds is greater than or equal to dq over t. Then we can combine that with the first law by saying that du is equal to dq plus dw, so we're going to be substituting for dq, du minus dw, and now we're going to take for dw, we're going to just assume that we have certain types of work. Remember, we had all the beta different types of work, so we're going to assume that we only have mechanical expansion work and materials transfer work in this particular system here. So we're going to look at a system of S substances in a single phase system, in a uniform single phase system. And so in this description then, we're going to substitute in for dW, the expression for PdV and for mu dN summed over all the S substances in this system. So all of these guys are divided by temperature here, so you can see then, work out how we got this expression by just substituting in those terms from that table of work. So this is for a uniform single phase with only PdV work allowed, all right? And in this picture here, mu is the chemical potential. That's the thermodynamic force that governs the flow of matter, and dN is the number of moles of the ith species of the S substances here, okay? Now, given this expression over here, we can also write just a generic differential form saying that, well, ds clearly depends upon the change in du, the change in dv, and the change in dn, where the n is the number of moles of the ith substance. So I can write down in a generic form, ds is equal to the partial of s with respect to u with v and all the number of moles of all the substances held constant times du, plus the partial of s with respect to v with energy and all the moles, the amounts of all the others held constant times dv, plus the sum of the partial of s with respect to each amount of the S substances with u and v held constant and all of the other substances where I is not equal to j held constant. And so and this is times dn. So from this expression here, we see that comparing it to this expression up here, that the partial s with respect to the derivative of s with respect to energy just corresponds to 1 over temperature. Similarly, we see that the partial of s with respect to volume corresponds to P over T, and we see that the partial s with respect to each number of moles of each of the substances there corresponds to the chemical potential of the ice substance divided by temperature. So we can make these identifications to these different partial derivatives, which will be useful later in this course. Now, we've written then entropy in this form here, because I'm just going to take this part here, just rewrite it again here. So this is the expression we have for the entropy. And we know that any thermodynamic process will proceed spontaneously as long as that direction causes the change in the entropy to increase. And once it reaches equilibrium, then we'll be in a situation where the change in entropy now will be 0. Okay, so at equilibrium, we expect ds to be equal to 0. And looking carefully at this expression, you can see that making this expression equal 0 means that we have a situation where du is 0, dv is 0, and dn is 0. So when the energy has stopped changing, when the volume has stopped changing, and there are no more chemical reactions changing, so in other words, the reactions have all reached their equilibrium, so dn, i's are all 0, there's no change in the number of moles of any of the substances, then we get a situation where ds is equal to 0. So we see that entropy is a natural function of these variables, the energy, the volume, and the number of moles of each, or the amount of each substance that's present. Now, we could experimentally, if we could, fix the energy and the volume. So if we could prevent the energy from changing and prevent the volume from changing, so we have this condition, then we could use this spontaneity condition to determine the direction in which that chemical reaction would go, right? So that would be a way that we could determine under these conditions here which direction the reaction would go. But the thing is, you may not be able to easily fix we already talked about volume, fix the energy and the volume. Those are not easy experiments to do in the lab, right? If we took that expression and rearranged it, so I'm going to take this expression here and rearrange it, I could have written it this way. So in this way, we see that the internal energy is related to entropy, volume, and the number of moles. So we have an expression where when we reach an equilibrium where the entropy stops changing, the volume stops changing, and the reactions stop changing, so the change in the amounts stop changing, then we reach a situation where du is equal to zero. So we see that the same spontaneity condition, which direction it will proceed so that entropy increases, also corresponds to a condition where the internal energy decreases so that we'll reach equilibrium once du goes to 0. So when the entropy stops changing, the volume stops changing, and the amount of each substance stops changing, then we've moved in a direction, a spontaneous direction, where we've reached equilibrium here. So what we're saying here then is that if we could fix the entropy so that entropy doesn't change and volume doesn't change, then we could look at a chemical reaction in this system with the entropy held constant, the volume held constant, and we can predict which direction would be the spontaneous direction for that chemical reaction. Now, again, trying to create a process that has a constant volume is not easy to do in the lab, and also creating an isenthalpic process is not so easy to do either. So this is true, but maybe not so useful for when you go into the lab and you want to predict which direction a chemical reaction will go. So what we do is we create a new energy function called the Helmholtz energy, and the Helmholtz energy is defined in terms of state function. So this harkens back to what we did with enthalpy. So we're going to define a new state function where it's u minus ts. This is a state function, t is a state function, s is a state function, so f is a state function. And if you make this definition, then you can show that df ends up being this expression here for, again, a uniform single-phase system where only PdV work is allowed. And written in this form, you see that the reaction will proceed spontaneously as long as df is less than 0, and when it will reach equilibrium when df is equal to 0. So that means that looking at this expression, when the temperature stops changing, the volume stops changing, and the amount of each substance stops changing, then we have reached equilibrium. So if we were interested in a chemical reaction where we held the temperature constant, so in an isothermal condition, and we held the volume constant, then we can use F to tell us which direction would be the spontaneous direction. So that's a little bit easier because now we have to just put it in an isothermal bath, but then isothermal conditions, but we also have to have a constant volume. So it's still not the best, easiest thing to do, but it's better than the previous examples where we had to have a constant enthalpy process. So let's go one more step further here, and okay, that's what I just said. So let's go one more step further, and let's define another energy function, this one using the enthalpy function. So we're going to do enthalpy minus temperature times entropy. So this, again, state function, state function, state function. So that's a state function. And if you use our previous expressions and substitute them in, you will get this expression here for the uniform single phase with only PdV work allowed. And what we see now is that Our spontaneous direction is the one associated where the direction that leads to delta G or dg being negative. So it will, as long as dg is negative, it will continue to proceed in that direction until it reaches equilibrium where delta G becomes 0 or dg equals 0. So in other words, looking at this expression here, when the temperature stopped changing, when the pressures stopped changing, and when the amount of each species, the number of moles of each species stops changing, then you reach equilibrium. So now we have a condition that's much more useful in the lab, because you can imagine working in a lab where you're under constant pressure, so you've enforced that this term is 0, and you're in an isothermal situation, so you have a constant temperature bath where you're doing the reaction, so you enforce this situation, and then all you have left is this term here, and you can determine which direction the reaction will go spontaneously by just the sign of what's left. So if the delta G is negative or dg is negative, then that's the spontaneous direction. If the dg is positive, then it's going to go backwards. All right. And again, this should be familiar to you. So for an isothermal isobaric process, then sorry, that should be P here. Sorry. And then that will allow us to determine, the which direction is spontaneous, and that's really of interest to a lot of chemists and engineers working under those conditions. So the Gibbs energy then is the state function that we consult when we want to know which direction is the spontaneous direction and which one's the impossible direction. It has brought into it both the first law and the second law and gives us all that information that we need. So because the Gibbs energy is so important, I'll just write a quick sort of freshman chemistry level summary here that if you integrate that expression there here, take the delta of that expression, you get this expression here. And so we see that for possible values of delta H in terms of their sign, possible values of delta S in terms of the sign, what are the signs of delta G, which is going to determine the spontaneous direction or impossible direction. And of course, temperature is always positive quantity in thermodynamics. So if delta H is positive, which is an endothermic process, and delta S is negative, which means that this is a process where entropy decreases, then we have a positive minus positive times a negative, which means that this is always positive, and that means that for this process, B to A is always the spontaneous direction. A positive delta G means that that process is impossible. So as we've written it, A to B, that process is impossible, but it tells us that the B to A process is the spontaneous direction. You have to flip it in order to get a negative delta G. So this process is the one that's spontaneous. This process, because of the positive delta G, is impossible. Going down the list here, you see that for delta H is negative for an exothermic reaction, and having a delta S that's positive, so the entropy increases, so that's negative minus a positive and a positive, means that you're always negative. That means that for this reaction, as it's written, it's always going to be spontaneous at all temperatures here, okay? And that's the same true for this one here, which I didn't mention earlier. But now you see when we get to a situation where delta H is positive, so it's endothermic, and delta S is positive, well then it kind of depends, because you can see if this is positive and this is positive, then whether it's the whole quantity is negative depends upon temperature here. If temperature is really high, then it will force this term, the T delta S term, to be the dominant term, and that will force it to be a negative value, and that will make A to B the spontaneous direction. But if temperature gets too low, then this term can dominate, and we will have the backwards direction, B to A, be the spontaneous direction. And then similarly, if you flip to enthalpy being negative and entropy being negative, then you see that that's a negative and that's a negative. Then again, we have a negative, and this whole thing becomes positive. So again, it becomes a bit of a battle, with T being the weighting factor here. So at high temperatures, what happens is that it becomes dominated by the negative. I'm sorry, it becomes dominated by it becomes dominated by this term, which makes it positive. And so we have B to A being the spontaneous direction. But at low temperatures, it becomes negative, and then we have A to B become the spontaneous direction. Okay. Now, the next thing I want to talk about is relating some of these partial derivatives. So this is just a little math review of something called Euler's reciprocity relationships, which tells you that if you have two state functions, x and y, and you derive some other state function from them, say f here, then you can write down, as we've been doing in the previous slides here, that the change of f is just the partial of f with respect to x with y held constant times dx, plus the partial of f with respect to y with x held constant times dy. And if we identify this as a quantity m, and this is a quantity n, we would write it this way. And so Euler's reciprocity relationship tells us that if you further take the derivative of m with respect to y, remember m is the derivative with respect to x, then it becomes the second derivative of f, first with respect to x and then with respect to y. Whereas if you do the derivative of n with respect to x, then it becomes the second derivative of f, first with respect to y and then with respect to x. And if f is a state function that's single valued and has continuous derivatives, then what we find is that the order doesn't matter, and that this partial is equal to this partial for this kind of expression. So this just gives us, this is just a simple proof to tell us that we can go back to our thermodynamic expressions and we can find relationships between these partial derivatives. So these are what help us discover what are called Maxwell's relationships. So when you have this general rule here, you might have an expression like this: du is equal to t ds minus p dv. You recognize that having this form here, so then you just identify who is the m, who is the n, who is the x, and who's the y, and you can, from this expression, you can derive this relationship between the partial derivatives. So I'll let you do more examples of this, but these will be handy as we're trying to relate how changes in different state functions occur during various processes in thermodynamics. Okay, so that's it for this video, and in the last video, we're going to be looking at the third law.